So I'll try to make it, let's say, shorter and give you the most important information on it. But before this description, allow me to remind some what I suppose is very principally important for the, let's say, solution and preparation of our nuclear power new generation to enter, as we call it, a second nuclear era. It means that we would like to study and to remind and recall the handicaps which were, let's say, since the very beginning involved in the so-called first nuclear era, and which was not allowed us to avoid, and which are finally proved by some accidents which we survived during this era. The most important, I suppose, is the very beginning of this nuclear power application, which started, we are very close to the 70th anniversary of the startup of first nuclear reactor, beginning of December 1942. And in that time, we know, all of us very well, there were only one possibility, the only one fuel available in that time, it was natural uranium. And to reach criticality, to put into operation and to keep the chain fission reaction, it was necessary to let's say, realize this first nuclear reactor system with the fuel in a solid phase, to have the highest density of nuclei, and of course to arrange it in the optimal, let's say, structure, heterogeneous reactor with the optimal grid and highest quality of moderator and so on. But the concept of solid fuel, this is from the very beginning, the, let's say, worst handicap of these nuclear reactor systems in the first era. What's more, the top brains from the team of Professor Enrico Fermi, who, let's say, organized this first step, entering the first nuclear era, and the conference, scientific conference on spring 1943, of course, in the time, secret conference, but nevertheless, they immediately expressed warning. They, of course, confirmed there is no other possibility in that time than use the solid fuel. But they expressed the warning to apply this concept in the industrial scale and even more in the global or massive global scale, because it is connected with the really high level risk, especially if the fuel was uranium and all the reactor systems were working in the uranium-plutonium fuel cycle. What's more, they immediately in that time, they recommended as soon as possible to shift to the concept of fluid, maybe in first stage liquid fuel, and as soon as possible to shift to the thorium-uranium fuel cycle. What's more, they immediately started to prove the possibility to develop such a concept and to solve all the problems connected, technological problem connected with this. You know that it was mentioned here, thanks to Dr. Xu, described in details this historical development. but you see, it is here confirmed that from very beginning they were going very fast to this goal. Unfortunately, the concept used in the first reactor and the other reactors, which was, let's say, very useful for them in the time, first order of goal, the development of a nuclear weapon, was leading to the first nuclear power plants utilizing this concept, at least in this low level of power, but afterwards, 1957, first commercial pressurized water reactor shipping port. This is the basis for the nuclear power in the first nuclear era. Well, I guess that the additional information was the development of the system with the liquid fuel in Oak Ridge Special Laboratory was already described here. It seems to me very important is that the first accident in the United States, the 3 Mile Island, was, let's say, giving to the stop of the further development of these new concepts and new systems, and the renaissance of these efforts starting at the beginning of 90s. So, but when it was stopped in United States, fortunately, the other countries started to go on with this. Especially, I should mention here the activity of Professor Furukawa in Japan, and he also initiated the activity in this field in Russia, and I was personally participating in the collaboration where the Russian program was collaborating with some Czech institutions and solving especially the problem of fluoride volatility process and this technology. You see here are the pilot line which was developed and manufactured in Czech and at the time Czechoslovak research and industrial basis, and installed, let's say, in the first half of 80s in the Russian Research Institute of Atomic Reactors in Dimitrovgrad, and was available for the checking of this technology in a relatively high level of capacity. The capacity of this line was reprocessing of 2 kilograms of heavy metal per hour. It was the heavy metal from the hot spent fuel from fast reactor. Immediately or few days after discharging from fast reactor, it was possible to reprocess. And you see on the scheme of this technology that this is very efficient, and giving separation by this technology is giving you 95% of spent fuel from conventional reactor, for example, from pressurized water reactor, totally the whole amount of uranium and the short-lived fission products are going out of the cycle, and the rest, all the actinides and long-lived fission products, totally it is 5% of the whole amount of this spent fuel, you are obtaining in the form of fluorides, which may be molten, and you have your liquid fuel for this molten salt reactor system. Okay, so backwards to this renaissance in the beginning of 90s. In 95, I was personally on the short study stay in Los Alamos National Laboratory, and afterwards started the collaboration between the Czech, in that time already Czech Republic was established, and this Czech research and industrial institutions, they're formed in 1996, National Consortium, and started there our national project Sphinx, which you see here. The consortium was led by Nuclear Research Institute, and the members were the industrial company Škoda Nuclear Machinery Branch, the Nuclear Physics Institute of Czech Academy of Sciences, and the universities. From the very beginning, it was the Czech Technical University in Prague, especially its Faculty of Nuclear Science and Engineering. And in the year 2000, Technical University in Brno joined this consortium, especially its daughter company EVM. And just recently, 2010, the University of West Bohemia in Pilsen, who is preparing and educating specialists for especially Škoda nuclear machinery and the operation of nuclear power plants in our country. Okay, so, and the project we started in fact after the establishment of this consortium in 1997 is called the abbreviation Sphinx. You have here the meaning of this: spent hot fuel incinerator by neutron flux, as I described, utilizing this fluoride volatility process for the front end of the fuel cycle. It is possible to use it for the, let's say, burning nuclear incineration of spent fuel from conventional reactors. You see, there are 3 stages of the project. There were 50% supported by governmental fundings, 50% was given by these members of consortium, which were of course interested in the final result of this development and are expecting they will be obtaining something back. You see here the scheme I've already shown, the detailed scheme of this fluoride reprocessing, and the pilot line, which was originally, as I mentioned, in Dimitrovgrad, but after Chernobyl accident 1986, the Russian activities in this field were stopped or temporarily interrupted. But in the year 1898-99, we moved this pilot line backwards to the Nuclear Research Institute in Czech and went on in the development and improving this technology in our own project. And of course, additional some technologies in this pyrochemical technology were added. Especially in the year 2004, we started to incorporate in this project, beside the function as an incinerator or burner, the function of breeder for application of this system in thorium or change over to the thorium-uranium fuel cycle. Well, at the very beginning, of course, we made some starting mathematical calculation on some simplified mathematical models of the system. You see here the cylindrical homogeneous reactor with the given composition of salt which is utilizing all the transuranium elements from the spent fuel from a pressurized water reactor with the burn-up level 40 megawatts day per kilogram. Okay, the thorium fuel cycle the scheme was added to this reprocessing, and afterwards, well, the results of these calculations you see here are giving the comparison. If you have here the selected actinides and the amount in kilograms or masses of these actinides in pressurized water reactor per the produced energy is giving just in comparison with the molten salt reactor cycle that this is the decreasing, let's say roughly on the two orders of magnitude in comparison with the conventional reactor. So, and now here you see the results of our calculations. What is the, let's say, not only production of uranium-233 from thorium, but also the great difference, practically very low, let's say, generation of transuranium in the thorium-uranium-233 full cycle. So this is very important parameter, of course, for the safety and the additional features of this new system. Okay, so we made at the very beginning the, let's say, some kind of optimization of the geometry of the system. You see here the, let's say, elementary module of our core is a hexagonal shaped graphite block, but in this there is a coaxial cylindrical tube in this graphite, and you see here the dependence of the, for example, multiplication factor on the radius of this cylindrical tube. There is the first maximum of the multiplication, which is corresponding to the fission on the thermal neutrons. And when you are increasing the radius of this tube, you are finally reaching the second maximum, which is given by multiplication on the, let's say, epithermal or resonance neutrons. So from this point of view, we started to make the concept of the elementary module, which is using the element fully equipped with the molten salt containing the fissionable materials from the spent fuel conventional reactor. So this is serving as a burner and simultaneously as a source of neutrons for the blanket, which may be used for the, let's say, incineration of long-lived fission products, or may be used for thorium breeding circuits. So this is, we will say, double or even multi-purpose system, which we sometimes call the Jeep, for the purposes which are very useful for nuclear power. Okay, so, and this concept now was finally experimentally verified. I will show you this is the proposal of the experimental reactor given like this, but we were not erected a special experimental reactor. We used our experimental reactor light water moderated, which was used for the development of pressurized water reactors, higher power limits, and we started to make the models of these elements and the core of the salt reactor. This is under the condition that this is full-scale model, but room temperature. So salt is not molten; it is in powder, of course, with some better conditions to have the comparable density with the molten, but the neutronic characteristics and processes are practically identical with the real and full-scale power one. So we made the measurements from the very beginning, the elementary. You see here how the module is inserted in the live water moderated experimental reactor. And finally, there were the measurements of this elementary module, as I mentioned, multi-purpose. You see, this is most important here, that the resonance group or the fast even group is relatively high level, even in the space which is filled by the salt composition. You see, this is the central element, and this black is the thermal neutrons, which are going very down here, but this fast and epithermal are relatively stable. So the efficiency for which we use this harder spectrum is relatively very high, and the same is in the field when we use it for thorium breeding by thermal neutrons. Of course, it can be possible to make even more complicated system, that we have this coaxial tubes, not only this smallest diameter, but central. So two purposes, even in this graphite blocks, is the two dimensions of this. Okay, this is one more module which was used, not inserting in the experimental reactor, but was irradiated by the neutron generator driven by a cyclotron accelerator, which is allowing to, this energy of the neutrons from this neutron generator is relatively very high, 20 mega electron volts. So this is much higher than in fast reactor, but we may adjust it by some moderator, layer of moderator to the spectrum of fast reactor or epithermal spectrum or pure thermal spectrum. All these possibilities are available here, and the measurements are showing here again the similar effect in this different. Well, you may notice that this is of course not made only for the experimental verification, for the basis for validation of computer code for this new system and so on. But you can imagine that during this process, during this the preparation of this experiment, you are collecting and accumulating your stuff, and especially not only in the research, but even in the industrial companies, by some technological experience, which is very, very useful for the other steps in the development of the, let's say, power and higher level of this system. Okay, so now few words on the international collaboration, and one more feature which was shown in the first nuclear era is that the finally, let's say, negative effects of the risk which is contained has a global, let's say, result, influence on the. So this is necessary to solve this and development of this new technology, let's say, in some a very, let's say, reasonable level of international or multinational collaboration in a global. So this was here, for example, a proposal of this global project of Gen 4, 2002. In the field of molten salt reactor, you know that in the year 2004 was decided that the molten salt reactor steering committee was established. Originally 3 members only, France, Euratom, and United States. And the year 5, 6, and 12 joined this activity Japan, Russia, and China with their national programs. So it seems to me that this is the very, very useful development of this basis. Okay, here is showing the result of our, let's say, again, incorporation of our national project in this multinational collaboration. So this year in May, there was given the French proposal of this utilization of these 3 types of these modules in the system for these 3 purposes, as I mentioned already, were made in our project. Okay. Well, simultaneously with this neutronic and reactor physics department, we were developing a relatively very rich program of the material and thermohydraulic technology connected with this new system. So there were starting the so-called Blanca group programs. First was small size probes, but irradiated under the conditions very close to operational in the research reactor. You see there are 2 probes or rigs finally. One is the size identical with the fuel assembly of this research reactor, and the second was identical size with the 4 fuel elements, fuel assemblies. Here are the detailed structure of the probe inserted in the reactor, but here are described the experiments already proved. You know, the whole system was designed to the maximum temperature 800 degrees centigrade, and this is, you see here, showed by measurement that the real temperature was between 600 and 700 degrees centigrade. And what is very important, that we may insert in the rig, let's say 5 probes with the different content, and here you see are the, for example, sodium fluoride with the melting temperature 995. So this is of course not molten in this lower energy, lower temperature, but the realistic composition, sodium fluoride plus lithium, pure lithium-7 fluoride with the melting point 670 is under these conditions molten, and you have here natural circulation in the probe, so you may make the first, let's say, first testament under the conditions close to operational, but very small size. One more feature in our conditions in Czech Republic, we can, if you have the fuel content containing the samples, we, after 48 hours of irradiation, reach already the limits which are allowed for our laboratories with the containing of the transuranium element. We made all this program in collaboration, close collaboration with the Kurchatov Institute in Moscow. So the same probes were afterwards irradiated in the similar research reactor in Kurchatov Institute, and the irradiation was prolongated up to 6 months. So this is, of course, very close to the operational conditions. You have afterwards analysis of the what the probe is containing after 6 months irradiation in the high flux. This is very, very similar to the operation of the power reactor. Okay, so the larger probe is 1/4 of this large model, because we use the symmetry. We tested this on the university reactor. You see here the results of the distribution of thermal neutrons and epithermal neutrons in such a complicated. So this is, of course, last stage of this is the testing of thermohydraulic problems and simultaneously testing of materials, structural materials under these conditions in small laboratory loop with, of course, not only containing samples of material, but also the simple components, pumps, and so on. And finally, the large size of the loop manufactured and operated in Skoda company in Pilsen. Skoda company also prepared a loop which was operated in a technical university in Brno for testing of full-scale components of such a, let's say, relatively very realistic. And now the final version is the loop which is prepared for the technical or University of West Bohemia for, let's say, not only research but also for education of new generation of the specialist nuclear engineering, especially for this industrial center. Okay, and this is the, let's say, proposal that if we finished all this testing and all this development, we may try to erect such a demonstration reactor. Of course, this will not be under the conditions of our own Czech Republic. We propose everything finished in the multinational laboratory cooperation as in the field of this global. Okay. Thank you for your attention.
Thank you very much, Professor Hron.